So our next speaker is Koichiro Ishibashi from the Advanced Wireless Communication Center in Japan. And his title has to do with perpetually reliable CPUs. So that should be very interesting.
Thank you for introduction. My name is Koichiro Ishibashi from the University of Electrocommunications. So today I'll show you, introduce a SOTB technology which enables perpetually reliable CPU for IoT applications. This work is done with the Low Power Electronics Association and project and Kyoto Institute of Technology. This is outline of presentation. First, I briefly show the objective of this work, and I will describe the SOTB technology and design strategy and experimental results and discussions for IoT applications.
So SOTB is silicon on thin buried oxide.
Yes, thank you. And so this is the image of the future sensor networks. So sensor networks are sensors are distributed to the environment to make the network. So there are many applications: power control, agriculture, infrastructure, and so on. So every sensor is connected to internet. So in this environment, most sensors should be operated eternally to form network. So this is the structure of sensor nodes, which consists of energy source, power stabilizer, and the sensor node. So in this sensor node structure, the operating condition should be efficiency times average generating power should be larger than the average sensor power. And so since energy source energy is very tiny, so the average sensor power should be small. So the to address this issue, intermittent operation is very common. So this is the image of intermittent operation. So for one cycle of intermittent operations, the CPU operates very short time, followed by the long sleep mode. Okay. So in order to reduce the energy, the operating time is reduced with high clock frequency, and the low sleep power is required, and high reliability is required because sleep time is long. So to address this, these requirements, we introduce SOTB technology. As you said, silicon on thin buried oxide. So in this structure, SOI layer is formed on the thin buried oxide with 10 nanometers. And body bias is applied from the silicon substrate underneath the thin box layer. So with this technology, the variability is suppressed to achieve the low voltage operation. And for the core circuit, we use SOTB devices, while the conventional CMOS structure is used for I/O circuit in 65 nanometer SOTB bulk silicon hybrid technology. So here is a power line structure of LSI using SOTB. So in the circuit, CPU logic. Circuit consists of CPU logic and data memory. And this VBB generator generates the body bias And at the standby mode, this body generator generates a -1 volt at sleep mode to reduce leakage on this circuit. So during a sleep mode, the leakage occurs in this logic and memory, and VBB generator also consumes energy, so that this VBB generator operates with a very low leakage. Here is the primitive cell structure. In the cross section, the P well and N well is isolated with source and drains of NMOS and PMOS transistors by the very thin buried oxide. And therefore, the leakage of body is around a few nanoampere level, very small leakage on the body. So on the here is a same micrograph of the primitive cell region. And we designed 9-grid height cell with 200 nanometer M1 pitch. And in order to reduce the noise occurred on the body bias, we used three-sided diffusion layers. And RDR layered concept is introduced to obtain the precise dot-lib libraries. So we have developed very high efficient charge pumps to generate body bias, which is dynamic substrate control charge pumps, DSCCP for short. In these charge pumps, these 3 transistors act as diodes. So this body of these transistors are controlled by this circuit using the SOTB structure. And so it achieves high efficiency. So the characteristics of a VBB generator is shown here at a supply voltage of 0.7 volt. It generates -1 volt. And the VBB generator consumes only 15 nanoampere. So we have measured software rate and for alpha irradiation and neutron irradiation. And in alpha irradiation, the software rate becomes 1/200 as compared to the bulk. So it is very reliable at sleep mode. And here is a chip micrograph and layout of CPU. It is 3 millimeter by 3 millimeter. CPU logic is located here with a 2 kilobyte RAM. And the VBB generator layout is 128 micron by 240 microns. So in the CPU operates at 28 megahertz with a 0.75 volt. It contributes to shorten the operating time. And its current is 90 microampere per megahertz or 14.3 microwatt. So it's a measured VBB voltage and the total consuming current. At the operation mode, body bias is 0 volt and CPU consumes 4.3 microampere. And at sleep mode, the VBB generator generates a body bias of -1.06 volt. And then the CPU current is reduced to 93 nanoampere. And VBB generator itself consumes only 15 nanoampere, and totally 108 nanoampere current consumption on total circuit. So I compare CPUs which shown in ISHC this year. So the operating power, we have good characteristics in terms of operating power and sleep current and operating frequency and software error rate. If we calculate the energy for intermittent operation for 1 second, it becomes 152 nanojoule, which achieves 100 nanowatt energy harvester operation. So this means that we can use PV solar cell indoor. So we have already demonstrated the operating demonstration system with this CPU. So in conclusion, I demonstrated the 32-bit CPU with using the 65 nanometer SOTB technology. So achieves these characteristics, and which enables a perpetually reliable CPU for IoT applications. Thank you for your attention.
That's very interesting and certainly very encouraging for the Internet of Things. And I just had a question. You have this acronym, well, it's silicon on thin buried oxide, but normally I think of silicon on insulator. How does it differ from silicon on insulator?
How's the different?
Between SOTB and SOI.
Okay. And so the main difference between the SOTB is a kind of SOI technology, but the difference is that the thickness of the SOI box layer, which is 10 nanometer, so that so we can, when we apply the body bias, the threshold voltage can be changed. So we control the body bias to reduce the leakage current. So this is the main
And that's
difference.
different from regular SOI. Yeah.
Yes.
Okay, thank you. Questions?
Yes, so I noticed this is, it's not a wafer scale. The box layer is patterned. It's selective. You don't have the same box layer everywhere. You show in the below that in some regions you have the very thin box layer. You have a hybrid. So other regions you do not have the very thin box layer, correct?
Yes.
Can you say a little bit about the process technology to form this very thin buried oxide layer?
So this box layer, it's initially it's a wafer. So we bought such kind of wafer. From the wafer company.
I see. It's a commercial. It is a commercial SOI.
Yes. Yes.
Wafer. Okay. Thank you.
Oh, I've got one. So I noticed in your diagram with the, go to the next one, or maybe, yeah, there. So the voltage bus is shared between the memory, the onboard memory, and the CPU logic. And I was wondering, typically you think of 60 or 80 SRAMs as requiring a higher standby voltage than logic and latches.
Okay. So in this work, I selected the supply voltage of 0.7 volt. It's a comparatively high voltage.
Yep.
So I use a common voltage for CPU logic and the SRAMs.
Is there any additional headroom if you decoupled the voltage buses?
Excuse me?
Would there be any additional savings if you decoupled those voltage buses?
No.
No? Okay.
In this work.
Actually, more than a question, it's not directly for you, but after listening at these sessions, I continue to find an incredible confusion between Moore's law and scaling. And the two things are completely different. in 2001, we reached the limit of the NAR scaling because we couldn't do anything that could go to beyond 130 watts. But for the last 15 years, Moore's law has continued like it had always done, and it will continue for the next 10 years. You can have as many transistors as you want, but if you operate them at high frequency, you'll melt everything. So the formulation of the problem has nothing to do with Moore's law. The formulation is very simple. You have two approaches. One, if you want to continue with von Neumann architecture, you have to find a transistor that consumed 100 the power, but can operate at the same frequency than CMOS. In that case, you don't have to do anything with the architecture. The other approach, you can use CMOS at very low frequency, and you can have as many as you want, but you have to change the architecture. So these are the two situations. And say the Moore's law comes to an end has nothing to do because I can guarantee you can build 10 billion transistors, just you don't know what to do with them. You can only use maybe 100 million, because if you activate all these others, everything melts. So it's nothing to do with you. But continue saying that we come to a problem because this Moore's law comes to an end is completely wrong. Moore's law can do 10 billion and will do 20 billion by 2020, but there's nothing you can do with it. The problem is frequency and power. You either unplug the CMOS and put something with very low power, a high frequency, or change the architecture and then use CMOS at low frequency and find something clever that can make everything work. Okay?
Well, Carlo, you're not arguing about whether there's a problem. All you're arguing about is the name of the problem.
Yeah. People work on the wrong stuff. Okay.
That's, I was hoping that someone would reply to Paolo, but that was a very good reply. Okay, so I think with that, let's thank all the speakers this morning.